All right, so we are going to continue where we left off last class, talking about significance testing. It's our newest type of inference that we're talking about. And so I'm going to go ahead and give a definition here for a test of significance. We're going to talk through a significance test, basically what we've already done, and then we're going to switch gears a little bit, talking about switching to t-scores instead of using z-scores, and again why we make that switch and that sort of thing. Okay, so a test of significance is used to test a claim about the population using we'll call it evidence, or in other words using statistics from a sample. Okay, and if you remember last time, we talked a lot about innocent until proven guilty and that sort of thing. So our null hypothesis at the beginning of these tests is always that the claim is true. And we're going to denote our null hypothesis as H of 0 or H naught. Okay, it's like our initial hypothesis, our null hypothesis. And that's always innocent till proven guilty, or in other words, that the claim is true. Okay, and then our alternative hypothesis which we will denote H of subscript A, H of A, is always a competing statement. So in general sense, it's always that the claim is false. Okay, or that the defendant is guilty. We saw last time, this was that the tax refund, the mean tax refund was less than $1,000. I think you had some on your homework where the mean time from 0 to 60 was more than 8 seconds, would have been the HA on that first problem on your homework, because the null hypothesis would have been that the mean time was equal to 8 seconds, and then they were trying to prove that it actually took longer than 8 seconds for the car to get from 0 to 60. Okay. We're going to come back to conclusions and a t-test in just a minute, but let's walk through a significance test, and we're going to kind of formalize the process a little bit from what we did last class. Okay, so I'm going to look at example C. It's about a package delivery service. It claims that it takes an average of 24 hours to send a package from New York to San Francisco. So this right here is the claim about mu. Okay, an independent consumer agency is doing a study to test the truth of the claim. This is like the prosecution. Okay, several complaints have led the agency to suspect that the delivery time is longer than 24 hours. That's going to help us a lot write our HA, our alternative hypothesis. Assume that the delivery times are normally distributed. Love that. With a standard deviation of 2 hours. Okay, pretty nice that they gave us that. And then it says for a random sample of 25 packages, that's our N, the mean delivery time was found to be 24.85. That is X bar. That's our evidence for the prosecution. Okay, so for now, we're going to call this a significance test. Just like when we studied confidence intervals, we're going to start with kind of a generic one, and then we're going to get into the specific types as we go today and next class, okay? So this significance test is about the mean. So we're going to start by defining that variable, because we're going to use mu in our hypotheses, so we need to know what mu represents. We're going to say that it is our true mean delivery time. Okay. And before I jump into conditions, which is kind of where we would naturally go based on our experience with confidence intervals, I have to state my hypotheses. This kind of goes along with your variables. So we're going to do our null hypothesis and our alternative hypothesis. Our null hypothesis is always innocent till proven guilty. So it's always going to be that we believe their original claim, that the true mean delivery time is equal to 24 hours. And then there should be some context clues in the problem that help us see what is it that the prosecution is trying to prove? What is it that we would like to prove? What is the competing claim here? And for this problem, the competing claim is that it takes longer than 24 hours. Or in other words, that mu is greater than 24. Okay, now we're going to do conditions. Same three that we're accustomed to: random, normal, and independent. Okay, does say random sample, so that's given. Given random sample of packages or of deliveries. Also given that the delivery times are normally distributed. And a sample of 25 packages means that we're hopeful there was at least a population of 250 packages. From New York to San Francisco, that feels completely reasonable. I'm sure there was at least 250, if not a whole lot more. So assume total of at least 250 deliveries. So samples are independent. Okay, so setup done. Now we have to actually jump into presenting the evidence for our case. Okay, and the two primary pieces of evidence that we're going to be able to present are a standardized score, in this case a z-score, and the probability associated with that z-score. Okay, so I'm going to calculate a z-score for the evidence that I found. The evidence that we found was a sample mean of 24.85. So we're going to calculate 24.85 minus the assumed mean of 24 divided by, and then I can't just use this original standard deviation. Because I took a sample, I need a sampling distribution standard deviation. So that sampling distribution standard deviation would be the original standard deviation divided by the square root of 25. I'm actually just going to do that whole calculation down here in my z-score. So the standard deviation would be 2 divided by the square root of 25. Okay, I could calculate that ahead of time if I wanted to. A lot of times it's easier just to do it all at once so that we don't use a rounded standard deviation. Okay, so I'm going to calculate this. All right, so I'm going to have 24.85 minus 24. And then I'm going to divide that by, and I'm going to make sure that I put this standard deviation calculation in parentheses, divided by 2 over the square root of 25. My z-score is 2.125. Okay. So I know that this sample mean was a little over 2 standard deviations above the population mean that we are, as of right now, believing is true. Okay, that starts to feel a little bit problematic. 2 standard deviations is pretty far, but we're going to need a probability to know for sure if it's far enough that we can go, oh, that 24 probably wasn't true to begin with. So we're going to do a probability that X bar is greater than 24.85. Because we're studying greater than as our HA, and because this is already above the mean, we want to know how far above the mean it is. So we want the right side probability. Okay, that's probability that Z is greater than 2.125, which we find by doing normal CDF from 2.125 to 99. Okay. And second vars will get me to normal CDF. Oop, did I just do? Of 2.125 to positive 99. I get 0.017. Okay. And that probability we always compare against what we call our significance level, which is assumed to be 5% unless we're told otherwise. But we need to write that down because people can't read our mind, okay? So our significance level, and the significance level, we use the variable alpha. It's a little a, looks like a fish kind of, okay? Alpha is assumed to be 5% or 0.05. Because anything smaller than 5%, we're saying, ooh, that is super unusual. That raises some red flags for us. Anything larger than 5%, we're like, it could have happened. Not that crazy. Not surprising. Okay. This probability, it's often called our p-value, probability value. Okay. Our p-value is smaller than 5%. So what that is showing us is that we no longer believe that the mean is 24. We have pretty convincing evidence that the mean is actually greater than 24. Okay, so our conclusion is first sentence. We're going to have two short sentences. Our first sentence is going to be that we either reject or fail to reject this null hypothesis. Okay. For this problem, because our probability is so low, that's telling us this is not really true. We don't believe it. Okay. So we're going to say we reject H naught, the null hypothesis, since our probability value is less than our significance level. I'm just going to put alpha. Okay. On our previous ones, we actually wrote out since our probability was less than 5%. Now, since we've written out our significance level, we're just going to put alpha there. Okay. Now, this conclusion right here is very, very technical. We want one that's more practical, that somebody can read and go, oh, okay, I see what you're trying to say. So we're saying since we rejected H naught, okay, that means I no longer believe this. That means I had pretty convincing evidence that the mean is greater than 24 hours. So that's what our second sentence is going to say. There is enough evidence to believe that the mean delivery time for all packages is, and then I'm going to put this into words, the mean delivery time for all packages is greater than 24 hours or is longer than 24 hours. Okay. So basically what we did last time, but kind of formalizing the process a little bit. We're going to continue to formalize it a little bit more. We're going to do even less of this writing in a second. Okay. But your process will be, stating the procedure, defining all the things that are kind of your setup, doing your conditions, and then you've got kind of your calculation phase, which is going to consist of a standardized score and a probability, and then you're going to write your conclusion. Okay. So let's look at letter D and make some adjustments to our process based on what we are given in letter D. Okay, because letter C, this example was nice, but we won't see them exactly like this very often for one main reason. We'll talk about that as we go. Okay, so letter D says that the vividness of visual imagery questionnaire, or the VVIQ, is widely used by behaviorists to assess visual imagery. Scores range from 16 to 80, with a lower score representing greater vividness. A group of St. Louis University researchers administered the VVIQ to a random sample of 51 college students on varsity sports teams. The mean and standard deviation of the VVIQ scores were 64.6 and 19.38 respectively. Let's pause there real quick. Okay. The mean and standard deviation here are from this sample of 51 college students. So this 64.6 would be X bar, and this 19.38 is S, the standard deviation from that sample of 51 college students. Okay, hopefully you guys are remembering that when I have an S, a sample standard deviation, rather than a population standard deviation, this is why we have to switch to using a t-score rather than this z-score. Okay, so kind of keep that in mind as we go. In the general population, the mean VVIQ score is 67. Okay, that's for everybody. So this is going to be our mu. Conduct a test to determine whether the mean VVIQ score of college athletes is less than 67. Okay. So again, that standard deviation coming from a sample means I'm using a t-score, not a z-score. So instead of just calling this a significance test, we now are going to get specific, and this is going to be called a t-test. Okay. Process stays pretty much the same, few minor differences here and there. Okay, still studying the mean, so we're still going to define mu. True mean VVIQ score for athletes. Okay, and don't forget your hypotheses go in this section as well. So the assumption that we go into this problem with is that the VVIQ score for athletes is the same as the general population, or in other words, that mu is equal to 67. And our goal as the prosecution is to prove that the VVIQ score is less than 67. Okay. Now our conditions. We were given a random sample. Given random sample of athletes. Okay. I was not told that this distribution is normal. And in fact, scores from 16 to 80 with a mean of 67 would not be normal. But I have a sample of 51. So my sampling distribution will be normal because of central limit theorem. So I can say that the sample is large, meaning greater than or equal to 30. So central limit theorem proves approximately normal. And then we took a sample of 51 college students. I think it's a fair assumption that they probably had a population of at least 510 college athletes. Okay, so assume population of at least 510 college athletes. So that samples will be independent. Okay, so we're going to get into our calculations here. And it's basically the same, but because of the S, we have switched to a t-score instead of a z-score. But our formula for our t-score is basically the same. It's x bar minus mu divided by, and then it's that adjusted standard deviation, which in this case will be S over the square root of n. Okay. And because we're working with t-scores, we're also going to need degrees of freedom. Still n minus 1, so in this case it's 50. And I'm going to go ahead and fill in my t-score here. 64.6 minus our assumed mean of 67 divided by 19.38 over the square root of 51. Okay. And then I'm going to show you kind of how we've been doing this in the calculator and how it would work. And then I'm going to show you a different way to do it in the calculator. All right, so we can calculate that t-score. So we'll type in 64.6 minus 67, and then we will divide by 19.38 over the square root of 51. Okay, and we get a t-score of negative 0.884. And since we're doing less than here, we would go to second vars, and instead of doing normal CDF, we would do t-CDF because it's a t-distribution. Okay, but it's the same idea as a normal CDF. Since it's a less than, we would be doing negative 99 to our t-score, which was negative 0.884. I didn't write it down, but promise that's what it was. And then our degrees of freedom is 50. Okay, and this would be our probability. Okay, so that's like doing normal CDF, except this is the t-CDF. It's a t-distribution. And that's fine. We can do it all by hand. Well, I say by hand, the calculator's still doing it for us, but each calculation individually. So here's our t-score calculation. Here's our probability calculation. But we can also ask the calculator to do both of those things at the same time for us, okay? So let me show you where that is. If we go to Stat and we go over to Tests, the second option right here is called a t-test, and that's exactly what we're doing. We're doing a t-test. So we're going to select number 2, t-test, and then it's going to ask us, just like our t-interval did, are you inputting data or are we inputting stats? I didn't put data in L1, so I'm not inputting data. I'm inputting stats. Okay, and then it asks us to tell the calculator everything that you know, basically. Mu with the little 0 next to it is your null hypothesis value. So that's going to always come from right here. That's 67. Your x bar was 64.6. Our S of x is 19.38. Our n is 51. And then this row right here is asking, what does your alternative hypothesis say? And sometimes this can be a little confusing as to which one we should choose. Wherever you see that mu naught, I want you to think of whatever number you've typed in right here. Okay, so this first option says not equal to 67. This option says less than 67, and this one says greater than 67. RHA says less than 67, so we're going to want to choose that middle one that says less than. Okay, and then we have two options. We can choose to draw or we can choose to calculate. I'm going to choose draw on this first one just so that we can see what's going on. Okay, it's going to draw, hopefully, there it is, the t distribution for us. Okay, remember this is a t distribution. And At the very bottom of the screen, you can see there are t-score and the probability value. They're the exact same ones that we got when we did it ourselves, but the calculator just did it all at once. It also is really nice because it kind of shows us 64.6 fell right here, and here's the probability of being at 64.6 or lower, okay? Most of the time, I don't look at the draw screen just because, I'll show you. The calculate screen gives me a little bit more information. So if I hit calculate, it gives me my t-score and my probability. It also reprints my x bar, my s, and my n, just in case I needed those for filling in this formula. That's especially helpful when you have data in your calculator and you need your x bar and your s. Okay. So our t-score, I'm going to finally write this down, is negative 0.884. And because our calculator gets both our t-score and our probability all at the same time, we don't have to write out all of the probability notation. Okay, we don't have to do all of this. We don't even have to write TCDF. We are just going to write p-value, which means probability value. And that probability value is 0.19. Okay. We do still need to write down our significance level, which we weren't told a specific one here, so we always assume, if we're not told, that it's 5% or 0.05. This probability is larger than 5%. So this probability is telling me there's a pretty decent chance of this 64.6 occurring, assuming that the mean really was 67. In other words, based on this probability, I don't really have enough evidence to say that this is wrong. Okay, so at the end of our trial, we can't prove guilty. We're just going to have to say not guilty. Or we're going to have to say that we fail to reject this. It very well could be true. We're not going to say we accept it, but we're going to say that we fail to reject it. Okay, so that's going to say we fail to reject the null hypothesis since our probability value was greater than our significance level. We did not find very convincing evidence. Okay, so we had to say not guilty. We failed to reject. So then our second sentence is always about whether or not we had enough evidence to believe the alternative. If our probability is big, we did not find convincing evidence. So we're going to say there's not enough evidence to believe, and we're going to write this out in words. There is not enough evidence to believe that the mean VVIQ score for all college athletes is less than 67. Okay. So the gist of this, we were trying to prove that college athletes' score was lower than the general population. Okay. We got a sample of college athletes, and this was their average. And that average was fairly close to the national average. So we did not find enough evidence to say that they for sure are lower than the national average. Okay. And just as a side note, lower scores are greater vividness. So we were trying to prove that they have a greater vividness than the population, but we weren't able to prove that. So college athletes, according to our study, are just like everybody else, at least according to vividness or VVIQ scores. Okay, let's talk T-chart and where that comes into play in this process, because I've got this T-chart, but I never even touched it. Okay, So this p-value, your calculator finds it for you, finds the probability for you. But your t-chart can confirm that that p-value is the correct p-value. And occasionally you'll be asked to just find it on the chart rather than finding it on your calculator. Okay, in which case you have to know two things. You have to know your degrees of freedom and you have to know your t-score. Okay, the negative won't matter because it's a symmetric distribution. So positive t-scores and negative t-scores have the same probabilities on either side. Okay, so we're going to be looking at the row 50 and we're trying to find a t-score that is close to 0.884. So I'm going to row 50. And my t-score of 0.884 is going to fall somewhere between 0.849 and 1.047. Okay. What I do from there is I go, okay, if my t-score falls between these two numbers, then I follow those two columns up to the top of my chart. And what I see is that my tail probability, or in other words, my p-value, was supposed to fall somewhere between 0.2 and 0.15. Based on my calculator, my p-value was 0.19, which does in fact fall between 0.2 and 0.15. Okay, so just a good way to check your work. You do need to know how to read this chart, and I'll point it out again in the next example. All right. Hopefully you're kind of following along, tracking with me. I'm going to, let's see. There is one more example I want to get through. I'm going to do that example, but first I'm going to put some definitions on the front of your outline. Okay, so back on the front of the outline, let's write our conclusions for our test of significance. There's two options. Your first option is finding the defendant guilty, which would be us saying that we reject the null hypothesis, and we would be able to reject a null hypothesis if or since our p-value was very, very small, meaning smaller than our level of significance. Okay, that'll be our first sentence. And then our second sentence will be, if we were able to reject something, if we were able to say that someone was guilty, we better have convincing evidence. So that's what our second sentence says. There is enough evidence to believe. And then you're going to write out whatever HA says, but you need to put it in context. Let me grab another pen. Hold on. So this right here will be written out in context. You won't just write HA there. You'll put it out in words, like the mean delivery time is more than 24 hours. Okay, that's the first option if you're able to say guilty or reject. Second option is we fail to reject H naught, the null hypothesis. So this is like saying not guilty, since, and that happens when our probability was not very small, since our probability is bigger than our significance level, which again, usually 5%. Okay. Second sentence, if we said not guilty, that means we did not have enough evidence. Okay. So there is not enough evidence Again, not enough evidence to believe the alternative. That's not how you spell believe. To believe the alternative hypothesis. Once again, don't write HA, put it in context. This second sentence is intended to convey to a reader who doesn't know AP Stats what your conclusion is saying. Okay, so that second sentence needs to be understandable by just the general population. Okay, and then a t-test. Let's go ahead and define what a t-test is, and then we'll do one more. A t-test tests a claim about the population, about the population mean, which is mu, using, and then it uses two things. It uses a sample mean, X bar, and a sample standard deviation, which is S. Okay, your formula is t-score equal to X bar minus mu over S over the square root of n. You also need to calculate degrees of freedom, n minus 1. You will end up calculating a probability value. Really, your calculator will do that. We abbreviate that p-value. And you also need to make sure that you list your significance level, which is alpha, and typically we assume that to be 0.05 unless the problem tells us otherwise. And the shortcut feature in your calculator to do this is found in stat tests number 2, which says t-test. All right. I am running out of time before my next class starts. I'm going to do that other example in a separate video, and I will post that one separately for you guys. Okay, you're welcome to try it without watching the video and then just kind of check your work. That might be a good idea. It has one difference in it. The alternative hypothesis is a little bit different than what we've seen before. Okay, but if you want to go ahead and give it a shot, that would be awesome. Otherwise, go watch the second video so that you can see letter E done all the way out. Okay.